Welcome, I am Keao, a maintainer of Keao. This is emulating block device incidents through I/O scheduler. More accurately, we are talking about the Linux block device elevator design and how we utilize it to emulate the latency or limitation of IOPS. We actually have tried to inject the I/O latency in multiple ways in the past few years. I will also talk about other attempts we have made in the I/O port emulation, and I'm pretty sure this is the best method we have found. So I would like to share with you. As I have said, we are talking about the emulating block device incidents, especially high latency. You may ask, why does it matter? Are the engineers in the so-called chaos engineering area or alarmist? The EBS of AWS has 5.9 durability. Why would I care the left 0.0001? However, the EBS only promises provision performance in 39% of the time. If you are using a physical drive on the bare metal server, it will be much worse, as the annual failure rate is around 0.9%. It obviously cannot support the SLA of your application. The programmers have designed a lot of strategies to handle the unexpected situations. Heartbeat, multiple replicas, auto translators, blah, blah, blah. However, even if your code can handle the situation when some of the machines are down or some of the processes are killed by accident, that doesn't mean your codes can tolerate the block device incidents. Consider the situation that a process can do anything unrelated with the storage, like responding to simple network requests. However, it will always turn out for storage-related requests. If you are a developer of some storage systems, are you still 100% confident that the fault-tolerant strategy will still work in this situation? Before entering the main part, I would like to introduce the company behind myself, the PingCAP. It maintains two open source softwares, TIDD, a distributed SQL database, and Keao, a chaos engineering platform. The TIDD tells us a lot of real-world problems we are facing, which makes the chaos especially good at reproducing the real-world problems. I/O operations is one of them, and for databases or for any other storage system, it's one of the most important, most risky fault they should handle. Let's start with the normal I/O operation calling path and see where we can find something to inject. In short, the process operates on a file through POSIX call, through memory mapping, through asynchronous I/O, or any mechanisms provided by the kernel. Then the file system gets the request and decides where to read or write from the disk. There could be multiple read or write for a single I/O operation on client, as the file system could be complicated and it has a lot of things besides the real data, like metadata needed to manage. Then the file system submits the I/O operation represented as PIO, which contains the start sector of the block device and related memory locations. After submitting the request to the queue, the so-called queue, the file system only simply waits for it to complete. But don't lose our target. From the whole process, you may have thought about several ways to inject the I/O latency or error without touching the scheduler. For example, considering the first step, if the process always does its I/O operations from read or write system call, we can use ptrace to pause the process for some time. If we find it's writing something, just like attaching a breakpoint at somewhere. Even if you don't know how, you can pretty sure you can do it through GDB manually or any automatically program. ptrace allows another process to get notified when the tracee is executing a system call and post the tracee automatically. The mechanism is usually using a debugger like GDB or some audit system or user space system call implementation like gvisor. We can also use it to inject latency to any system call or user function calls. However, it cannot solve all I/O situations. If you are submitting the I/O operations through a mapped address, you are writing to a mapped memory, but it cannot be cached by the ptrace. Another consideration is that the AIO, if you are submitting an I/O request through I/O submit syscall, the behavior definitely shouldn't be a synchronous delay. The performance overhead of this method is also unbearable. It will slow down all system code. Another problem is that it cannot simulate the behavior of page cache. Reading from the page cache shouldn't be delayed. Okay, then let's see the second step. There is also an opportunity to inject latency. We can set up a hook file system to inject latency. The file system can be implemented to be slow and allow us to specify the latency. That's exactly what we have done in the past few years. It's a relatively good solution, I have to admit. The roadmap is quite simple, and the user space file system is also a proven technology and has been used in a lot of different places. Last year, I presented a talk, Test Application Storage Stability by Injecting Storage Errors, also in the Percona Live Online. In that talk, I discussed the implementation of such a file system and how we reduce the overhead by dynamically replacing the file system inside a container. You can find the record of this presentation on the YouTube or Percona Live website. So I will only give you a brief introduction to this method. Take reading for example. The read syscall will be serialized as the user space file system request to the Keao and the Keao as the user space program will read the file in another folder to give you the correct response. From the technical point of view, the overall architecture is pretty simple, but the implementation has produced tons of the bugs. Writing a file system, even if it's only a virtual one, is really hard. The code base grows rapidly and soon becomes too complicated to manage. Except the file system, we also use ptrace in the project to replace the open file in the target process. And that is also easy to break. The performance overhead is also significant, as it will copy the data between user space and kernel space multiple times. After describing the two methods we have tried, let's dive further. In general, the deeper layer of the I/O stack, you will get less information about the user space application. You will not know which file is operating, which path is reading or writing. Meanwhile, the abstraction becomes much simpler. Every operation turns into a relatively simple request. It means if we could inject latency in the fourth or fifth step in this pipeline, we will not be able to inject latency to a single folder because we are not a file system. We know nothing about the file system. I don't know the path it's writing. But you could still inject latency to the whole disk. Most of the time it is enough, right? Let's see how it's finally implemented. See step 4, the theme of this talk has already been there quietly, the request queue. Yes, the request queue is just a scheduler. It's a data structure to store the requests, then the request can be merged delayed, sorted in this so-called request queue. According to your needs, the scheduler doesn't have to be a queue, it's just inserted one by one like a queue. For example, if you want to sort the requests according to the sector so that you can merge the near requests, then you could use the arbitrary instead. To extend our understanding of the scheduler, we should also know the output of the scheduler. Yes, that's the hardware driver. The driver can dump a request from another queue. This queue is not the same with the previous request queue, so we call it hardware queue for distinction. The driver will read the request from the queue, from the hardware queue, convert it to something that the hardware can understand, like an NVMe request, and finally send it to the hardware through something like PCIe memory mapping and map the queue inside the memory so you can write the request in the memory. The output of the scheduler is just pumping its request to this hardware queue. In general, a modern multi-queue scheduler framework is something like this. The red part in the graph. There are many hardware queues. The number depends on the NUMA nodes or CPU counts. The elevator usually creates one data structure for each one of the hardware queues to make it faster, but lost the ability to schedule between these different data structures. Different data structures and different pumping strategies give us different schedulers. We are using this framework to inject latency. As all requests are stored inside the scheduler, we can delay them for any long time. We call this evil scheduler the IOEM. It means the IO emulator. The source comes from the NetEM, which is a network attribution emulator. It can be used to emulate the network latency, packet drop, or anything else. IOEM is here to emulate the I/O latency and IOPS. The behavior of this scheduler is quite simple. It stores the requests and assigns an expected schedule time for all of these requests. When the hardware queue wants to get a request from the IOEM scheduler, the IOEM can pick up the earliest possible request to see whether it has met the time to give it to the hardware queue. To both add latency to the I/O operation and limit the total traffic, we use the arbitrary as an internal data structure to help us to know which request has the earliest time to dispatch. IOEM also has a global traffic limiter, which maintains a counter to record the time of I/O operations of all queues. Remembering that there could be multiple hardware queues, so we have multiple arbitrary set lists. The whole process, as described in the former slide, has two sides. When a request arrives, we will calculate the expected send time for it and store the request in arbitrary sorted by the send time. When the time arrives, it can be stored in the list once the traffic limiter allows the request to go out. It can be dispatched to the hardware queue to set the request as early as possible. We set up a timer to periodically ask IOEM to check whether it can dispatch the request. After registering this scheduler, we can use FIO to test the IOPS. You can see the I/O limitation is really cool. The result of FIO is so near with what we have set. In this example, we only allow 1005 requests in 100 microseconds. And the result is expected, 14 to 15 kilo IOPS. Not that accurate, but it's still cool. I still do wow every time I use it to test our databases. The most fascinating thing is that this injection can be modified at any time. You can change the latency, limitation, and any time. You can even change the scheduler to another one to make sure your application has returned to a normal state. It matches the spirit of chaos engineering. This injection enables us to inject latency in production environments. There are also other tools that can work on a block device layer, for example, the device mapper. We already have a device mapper to add a delay before writing it to the backend device. However, it cannot be modified at any time after the application has started. Above all is the implementation of the IOEM and the kernel modular. However, there is one more thing. If you know Keao Smash, it's a chaos engineering platform running on the Kubernetes. How could we combine the so-called low-level things with the super high-level Kubernetes application? It's also a long journey before we can get the real FD of the block device used by the pod. On the Kubernetes level, firstly, we have a pod, then we can get the volume from the pod. Now we can handle two situations. If the volume is the host path, then we can find it. If it's a PVC, then we have to get the related PV and get the corresponding block device for partition or directory. In conclusion, we can get a directory or a block device or a partition. Then we continue the processing on the nodes. On the nodes, if we are injecting a directory, we can get a block device or partition. If we already have a partition, we shall turn it into a block device. Finally, we can automatically modify its elevator and inject latency. The evil part of this implementation is that we transparently inject latency to the whole block device, and we cannot separate different partitions or folders. After all of this encapsulation, the user can simply apply an IO injection through a simple YAML file. That's nearly all of this sharing. Finally, I would like to share the current status of this project. The related kernel module has been implemented in this repo. It's compatible with CentOS 7 3.15 until the 5.15 LTS mainline kernel. We have done a lot of work on the compatibility, and there are still a lot of our users are using CentOS 7, which sounds not great. The Keao Smash integration is still in reviewing. Sincerely hope it can be merged in June or July so it can be published in the 2.3 version of Keao Smash, which is scheduled to be released at the end of July. We are also trying to submit a kernel patch to the upstream. It's really necessary after 5.16 as some needed header files are not public anymore. We will need to eliminate something related with the cloud of Keao Smash and complicated filters and provide it a simpler way to configure it. And then we can send it to the kernel-related maintainers. Really hope we can meet IOEM in the mainline Linux in the future. Thank you. That's all for this sharing. If you have any questions, feel free to ask. I believe I was there prepared to answer your questions. If you have any further considerations, you can also contact us through the Slack channel, GitHub issues, or discussions. We're really having a lot of fun breaking other computers or servers. If you are also interested in chaos engineering, so maybe we can play together. Thank you. That's all.
Hi, everybody. Welcome to another Haas Talks Foss. I'm here with Liquan Pei from PingCAP. How are you today, Liquan?
I'm pretty good, and I'm pretty excited to take this conversation with you.
Great, great. And so tell us a little bit about PingCAP and what you do there for those who might not know about PingCAP or TiDB.
Yes, PingCAP is a company founded in 2015, and it starts with a project called TiDB. And TiDB is, I would say, a NewSQL or HTAP database. For people who don't know about HTAP, it's a short for hybrid transactional and analytical database, which means that you can process your ORTP workload or ORAP workload in a single system. And since then, since it's funded and it starts with building the open source project, and it has attracted, I think, over 2,000 stars, and it has already over 1,000 contributors of the project. And it has been used by many companies. I think we now have over 1,500 companies has adopted TiDB in production. In short, I think TiDB is a new distributed architecture. It was inspired by Google Spanner, and it has a layered architecture. Yeah, we can go more detail about that.
Okay.
And I'm doing, I joined PingCAP in 2020, but I've been know this company a long time ago. I know the founders since the year of 2017, at that time I was at Pinterest, and we have a project, and we call it like real-time indexing. And actually, that's a good fit for TiDB. We did a quick kind of like a demo at that time. I think that is how I know about TiDB at that time. So that is kind of like some of history with TiDB. Now I'm here work as database engineer. But I do know in startups, especially we are still early stage in the United States. I also wear multiple hats, and
Okay.
I did help with the recruiting a lot. I interviewed maybe a couple hundred candidates last year and this year. And then I also worked very closely with a few customers, especially some key customers in North America.
Yeah, and many of the former people who I've worked with in the past have gone on to work at PingCAP, many from the MySQL space because PingCAP's protocols are MySQL's protocols. They've
Yes.
made sure to mirror those so there's a compatibility with existing MySQL workloads.
Yes, that's a good point. I think when we build that, I think we keep in mind that we want to be MySQL compatible. I think that is kind of the original goal, because we know that MySQL is kind of the most adopted open source database, and it has a lot of usage. And I think when the founders start build TiDB, they want to make the migration easy from MySQL. Yeah.
Yeah, and we've seen that, in this new SQL space, you've got, TiDB, you've got Yugabyte, you've got Cockroach. Yugabyte and Cockroach have chosen the Postgres protocol versus the
Mhm.
MySQL protocol.
Mm.
So, depending on where you lie on whether you prefer Postgres or MySQL, there is a solution for you.
Yeah.
But maybe tell us a little bit about what new SQL is, because people are using MySQL today. They understand it. Why would they need to move to the next level to this new SQL version that has more features? What do they get from doing that?
Yeah, I think that's a good question. My understanding of NewSQL is really combine the advantages of the relational database, which has a transaction capability and the SQL interface, right? And the scalability of NoSQL, right? Because NoSQL excels at scaling. It's pretty easy to scale. You can add nodes, and it can handle more, can store more data and handle more traffic, right? That is kind of what NoSQL excelled at. Whereas for traditional relational database, you have the transactions, right? This simplifies a lot to developers because they can safely retry when something fails. Whereas if you don't support transaction, then you have to do a lot of additional work in order to make things correct.
Yes.
And that's one point. And the other thing is that a SQL is much easier, right? It's very expressive. You can do a lot of computations using SQL. You can do scans, you can do group bys, you can do joins, and then do analytics, right? You can do a lot of things. Even you can build machine learning libraries using SQL. So I've been working at a previous company that they called Greenplum database, and they actually build machine learning library on top of SQL. So you can do a lot of things with SQL. So this definitely can speed up the developer velocity. So I think that benefits. However, traditionally scaling a SQL database is pretty hard, and people choose to use sharding. And once you go there, and the application needs to be aware of the database sharded, and you lose the transactionality across shards. So I think with NewSQL, the sharding is transparent to the user, and the user still think you are working with a single node database, but the database underlying can be scalable. You can add new nodes, and then you can move the data around and automatically. And by adding new nodes, you can scale the database, serving more traffic and store more data. So I think overall, from the benefits to the developer is that, first of all, they're still working with SQL, and they are still mostly thinking it's a single node database. Then they have a higher developer velocity. And from the maintenance point of view, and you don't need to manage the sharding, and I think that is kind of the benefits.
Now, one of the interesting things about TiDB is it is currently a completely open source, product. So anyone can go out, try it, use it, and get the benefits of this new SQL for themselves. But you can also contribute to it. You mentioned that you have thousands of contributors worldwide.
Mm-hmm.
So it's a bit of a different model than a lot of companies are following. A lot of companies right now tend to, prefer some sort of proprietary-ish or not quite open source license, if you will. So, that's one of the exciting things about that, and that can help, definitely drive adoption. But, I talked with Morgan on our podcast, Morgan Talker, not too long ago, and he was talking about some of the hackathons that, the engineers at PingCAP have put on for their community. And I was curious, have you been participating in those hackathons as well?
Unfortunately, I didn't, but I would love to.
Okay.
I think it's a pretty. I think it's a pretty fun fact. Actually, I watched a lot of videos, and a lot of articles talking about the hackathon. For example, using GPUs to accelerate or AP processing, and building a graph database on top of TiDB, right? Or building a file system on top of TiDB. There's a lot of interesting ideas. And also there are some features that I think customer really want, like the TTL in tables, right? This is a lot of customer want, and a lot of interesting stuff. So, yeah, I would love to do that, but I think the challenge with me, the time zone issue, really in the US, I think there's a lot of events actually in the APAC region, so that's kind of what I miss those things. I hope that we can have a hackathon in the local time zone so that I can really participate. But there are a lot of interesting things out of it. For example, for the GPU kind of acceleration, NVIDIA also expressed some interest in knowing more about it and see whether we can collaborate in some sense. Yeah.
So your job is working heavily. You mentioned you're doing a lot of different hats because you're a startup, but officially it's working on the database kernel itself. Is that correct?
Yes.
So what sort of work are you doing recently? What sort of interesting things are you looking at?
Yes, I think one thing I was now looking at is kind of some new features in the database. For example, whether or when should we have dual partition in TiDB, yeah, and how to make TiDB more cloud native. This is something I was involved in the discussion. So, yeah. So those
and you're talking about cloud native in terms of being able to run on Kubernetes, automatically spin up new nodes, reshard, repartition as you need to?
Yeah, this is part of it. Also, I think another thing we need to look at is that how do we build a database that leverages the cloud primitives? For example, I can give you an example. For example, right now, the techy way is using Raft to do data replication, right? And when a node is done, when I add a new node to the system, you actually need to copy the data from the existing node to the new node so that you can serve the traffic, right? So
Yes.
that is current like architecture. But then in the cloud, you have S3s and you have other like the cloud services available. And then you can leverage that to simplify those replication. So for example, you don't have to replicate all the data. You can probably replicate your logs, right? That's enough. And the all the rest can be done through the S3, right? You can use S3 and then to download. And another thing you can leverage as the cloud is that typically the TechAV is doing compactions because they are building on RocksDB. And periodically they need to do compactions to kind of make the data more better formed, I would say, right? To deduplication, to make things like more structured. So, and that is done traditionally in the same TechAV nodes as in the nodes serving the traffic. And then when you do compaction, it can have impact on the online traffic, right? However, on the cloud, you can do things differently. You can actually do remote compaction. You can, okay, so you can say that, okay, I have a few dedicated machines, and then we can ship those files in those machines and do the compaction and ship them back. So at the end of the day, though, the machine serving the traffic will consume much less CPU when doing those compactions. You actually offload the compaction into dedicated resource, and as a result, it causes like a much more stable performance to the online traffic. So those are some kind of things, the benefits of the cloud native architecture, right?
Okay, so I mean, yeah, I mean, it sounds like a lot of the stuff you're working on is kind of twofold, right? Obviously, the performance and scale is always important, but also those operations, making it easier for things to happen behind the scenes. I know that trying to spin up new nodes is always a challenge, and yes, if you can hook into some of the things that are already available in the cloud, whether they're block storage, copies, or do snapshots, or take your backups from S3 wherever. Those are always good things, and obviously anything that you can do to speed up some of the back end maintenance is also going to be helpful. But when we talk about like use cases, and you mentioned TiDB has 1,500 customers, and probably 10 times the number of users. I'm curious, is there a use case that you see that this is really popular with? Is there one or two different industries or different workloads that TiDB really excels at?
Yes, sure. I think we have like customers in the fintech space, and the customers, I think I want to maybe give it two use cases. I think one are in the fintech domain, and the other maybe in the SaaS domain. So I think for the fintech, that there's nowadays more and more like I would say that either online banking or there's P2P or customer-facing payments, right? For example, Venmo, Square Cash App, and there are other I believe companies in different parts of the world. For example, there's a company called New Bank in Brazil. They are sending, they are offering credit cards, and there's another company in South America called B89. They are offering also similar to New Bank. They are offering the credit card to Spanish-speaking like customers. So I think for those companies, they want to offer good experience to the users, right? Because they are dealing with a larger user base, yeah. And I think they are have the challenge of scaling their business. For example, one of the customers we have is in Japan, and they are an online payment company, and you can basically send money to each other. And they have met the challenge that, okay, they cannot scale during peak hours, and especially during promotions. And then they are suffering a lot about that because the scale database they were using cannot scale the rights, and then they basically cannot do the promotion. The database is done. So since they decided to use TiDB because TiDB's architecture is a master, and you can scale both read and writes. And then once they migrate to TiDB, they no longer suffer any outages when they do promotions, and TiDB can easily handle 3 times of their current scale. This is one of the examples we have, which is a fintech, the online payments, and you are offering a service to the consumers, and they can do a lot of transactions at the same time, because of it's a consumer-facing app. That's one
So
example.
fintech is an interesting space because it's one of those spaces that when you look around the industry today, everyone is concerned about, ensuring that not only do they have performance, but security. And in fintech, it's one of those things that security is even further along. So maybe tell us a little bit about, some of the things that you're working on from a security standpoint to make sure that, the code that's going out there in the feature set can handle a bit more of a secure environment like that.
Yeah, sure. We have like the TLS between all the components and the client and the cluster. Okay, and also we have encryption at rest, which call also TDE for our storage layer. And then we have also authorization and authentication system in the TiDB layer. And beyond that, I think we also offer audit log for the users that they know what happened in the database. So here are some features we provided in the database itself. On the cloud services, you know that we probably I should mention that we also offer hosted TiDB. We call it TiDB Cloud. And for that, we have actively kind of like doing compliance stuff. So for example, we have passed SOC 2 Type 2 and also the ISO 27001 recently, and to show our continued investment in the security.
Okay. Yeah, I mean, it's always interesting to see because the bar for not only performance but security keeps on becoming, bigger, higher and higher to clear as these systems become more critical, especially in some of these ancillary spaces.
Yeah.
But from an engineering perspective, I am curious, like what are some of the interesting, maybe fun things you've uncovered looking at the code base, for TiDB? Are there certain things that surprised you when you started to dig in? Were there things that you thought were very interesting, or that you think is pretty unique?
Okay, pretty unique. Okay. Yeah, I think the pretty unique thing is usually when you work with a distributed system. Some pretty simple thing can be really complicated. So that's one thing. I won't give you an example called, I'll say the bin log or change data capture, right? And I think if people has worked with MySQL, and they should be familiar with the bin log, right? And the bin log can be used to do data replication, set up like a the primary, secondary like architectures, right?
Yeah.
So those are interesting. And I think for a distributed database like TiDB, and then if you do bin log change data capture, there's a lot of like interesting problems you may never think of when working with compared with working with a single node database. For example, because TiDB supports distributed transactions, and all the transactions can happen on different nodes, right? And if you're doing a change data capture or a bin log, you can gather this data from different machines, right?
Mm-hmm.
But if you really want this data to be useful, you do need to output the data in the transaction order so that you can build like a primary, secondary architecture, build your DR system, right? However, then there's a challenge is that because everything is distributed, you get a lot of things like in the order of modifications, but not in the order of commits, right? You can start a transaction, and this transaction can be very long and can then committed very late, right?
And
Right.
span multiple nodes.
And then even you don't know when you receive everything, right? Because everything is distributed. You don't know, okay, whether I have received all the updates for this transaction, right? Then this really becomes like pretty interesting. So I think for the distributed kind of transaction, we actually utilize research actually from big data. I think there's a paper called NAIAD published by 2013 by Microsoft that they're actually building a data flow system and using the
Okay.
concept of the result timestamp. And the idea of result timestamp is that you know that before this, once you receive this, it's like a watermark in the stream processing system, telling you that once you receive this event, everything before this timestamp has been received by the downstream. Then you know that all the events are you receive all the events, then you can send them to the downstream. Other than that, you cannot send to the downstream. And this is pretty fascinating. And without this idea, you cannot really reconstruct your transaction order, right? So I think this is something I really like.
Yeah, that's interesting. I mean, in when you think of a distributed system and a distributed, SQL system, for those of us who have been in the database space, you're used to being able to monitor nodes, even if there's multiples in a cluster. But because of the distributed nature of the transactions, it can lead to other issues, not just with the, trying to piece together, the transaction logs, but also the observability has in the monitoring and being able to figure out, which potential node might be having issues or, trying to piece together that has to be a challenge from a back end perspective as well.
Yes, I think I totally agree with you. So uh, I think the challenge with distributed system is like you have to deal with failures, right? So you have to deal with failures, and you need to make sure that your system behaves correctly with those failures. So and then also because it is kind of like handling a lot of things at the same time, right? So those are understanding what happens is pretty challenging, especially where support like SQL queries, and also we support complex SQL queries, and figuring out what consumes the most resources. It's kind of challenging. Yeah.
Yeah, and I mean, I can imagine that it's hard enough sometimes to find the problem area and
Yeah, and also you know that there are there's a lot of kind of like background works like compaction, like the garbage collection, yeah, like the synchronization between the column store and row store, right? There's a lot of backend, and then the replication, then the transaction logic, right? It's kind of like a lot of things going on at the same time, and beyond that, there's constant failures. You do need to move data around, and you do need to understand the environment in all this kind of dynamic in this very dynamic environment, and ensure everything is correct, even with all this dynamic correct. Imagine the case that you still want to support ACID, right, for all the transactions, given that the data is constantly moving, there's constantly failures, there's constantly retries. So there's the region splits, region merge, right? So that is kind of what really I do really like.
Yeah, I mean, it's fascinating because as you start to go in as a database person, as someone who's running this, to be able to understand where a problem is, where the issue is always that interesting step that from an engineering perspective you try and fix those without escalating them up or letting people know about them, but eventually someone's looking for
I think that's the beauty of the database. You hide a lot of complexities inside, right? And for the user see, okay, I think we are just running SQL. And I think for a lot of like, I'll say, I've been working with people from other, working mostly in the upper level in previous companies. So they are really mostly dealing with the running SQL queries, not writing SQL queries. They would think that SQL system is pretty magic, but I mean, for a database person, it's really like they had a lot of complexity there. So
yeah. Ah, very cool. Well, Li Quan, I want to thank you for stopping by and giving us a little bit of an overview of TiDB and some of the things you're working on. Always good to catch up. Appreciate you stopping by.
Sure. Thank you.
Wow, what a great episode that was. We really appreciate you coming and checking it out. We hope that you love open source as much as we do. If you like this video, go ahead and subscribe to us on the YouTube channel. Follow us on Facebook, Twitter, Instagram, and LinkedIn. And of course, tune in to next week's episode. We really appreciate you coming and talking open source with us.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.